Well, hello, NATR 346, and welcome to part 2 of the two-part stream talk. The first part we focused on erosion resulting from surface runoff, and also introduced the concept of streams as essentially conveyor belts of earth material taking newly formed mountain material and carrying it out to sea to keep as part of the rock cycle. This talk is going to focus on how streams carry water and floods and the relationship between rainfall and runoff. And so what I have here on this slide is pictures of culverts, and these are simply large pipes that are designed to divert a stream underneath a crossing, say a road or a pathway. And I'm starting here because this is how, engineers use hydrology to try to figure out how to size a culvert. Typically, when I see a culvert, there's usually just a trickle of water going through at the bottom, and you might wonder why these culverts are usually so large. And it is because they have to be designed to carry not just the typical flow of a river, but also a large flood event, maybe a 50-year rainfall event where the river stage is large and this pipe needs to carry a lot of water. So the main tool that developers, engineers have is just to oversize this thing, because the last thing you want is for the river to overwhelm the system and wipe out all the infrastructure. Another clever approach is to take other culverts, put them next to the main one, and so that when the river reaches a certain stage, these can engage. But I start with this to contrast it with how natural systems deal with this problem. The problem is a river needs to carry water. It's got the business of carrying the water year-round. A lot of times a perennial river will be fed by groundwater, and if it rains gently, then this river will carry a little bit more water. That's fine. But when we have our winter season, and we can have some very large storm events that don't occur except for every 10 or 50 years or 100 years, how does the stream deal with that? Well, in the natural system, the stream relies on its floodplain. And so we call it flooding, but really flooding has a bad connotation. The river has actually shaped its form in this alluvium to be designed such that it will typically carry water in this base flow formation, but it'll have a floodplain at the ready for large rain events. And in this diagram, there's this low level, and then there's this medium level, and this is where the real flooding might occur, at this bank full elevation. So this is a term that's unique to hydrology, and it's important to know for us. I'm going to ask you questions about a river that's at bank full elevation and how much water it's carrying, and whether or not the next storm will cause a flood, just to kind of get used to the terms here. So again, this is just another simple diagram about how natural systems work with rivers. You'll have a regular channel. Over time, the river may form what's called a natural levee. It's just the physics of how the water carries the load, and what happens when it overtops the banks. It tends to deposit some material here, and so you'll see nice little natural levees, and then behind those a floodplain. Here's another diagram of the same thing. You have the flood stage or bank full discharge. This actually color should be all the way up to here. This would be bank full, and then after bank full discharge, you get to flood stage. And as this flooding occurs over time, natural levees get built up. Here's another kind of nice diagram about that. Now, I'm sorry, this one's blurry, but it's the same thing. This is some terminology about rivers and how they carry water. The deepest part of a channel is called a thalweg. I have no idea where that came from, but you'll see it in textbooks. And if you want to sound like you kind of are checked out on river systems, you could say, hey, check out that thalweg. It's just the deepest part of the river, and you can walk the river and follow the thalweg down. Then there's the water surface, and then here is bank full stage. This is where the water rises up to the point where it's going to overtop its natural levees and use the floodplain to carry that extra water. So for straight hydrology, this is a very important diagram to be familiar with. And lo and behold, yes, another equation. Sorry about that. But this equation states that the discharge, the amount of water that's moving through a river, is equal to the area of the water in a cross-section times the velocity of that water. And the units are cubic feet per second. And again, I'd encourage you, I do a much more detailed write-up of this and some practice problems calculating discharge. But just like the fundamental unit of water for irrigation and for watershed management is the acre-foot, the fundamental unit for flow in a river, called discharge, is the cubic foot per second. So you have the depth of the water, that's in feet, the width of the water, that's in feet, so feet times feet is square feet, and then you've got the velocity of the water in feet per second. So feet times feet times feet per second is cubic feet per second, CFS. And a cubic foot is about the size in rough terms of a basketball. And so if a stream is running at 30 or 40 CFS, that's like 30 or 40 basketballs barreling down this channel. So hopefully by the end of this unit, you're going to be comfortable with this relationship and this unit. And this is a diagram that's out of the USGS publication in Unit 4, kind of how they measure discharge. They take a current meter, so you got a stream here cruising along here, and they'll divide up the cross-section of the river into little segments because the velocity in each of these segments can be different. Like the velocity of the water around these banks here is slower because it's getting churned up and friction loss along the sides here, whereas the velocity right in the sweet spot in the middle of the river is faster. So they divide up the river like this and put in a flow meter and measure the velocity of the water and add it up and divide by the area. But more detail than we need to know. Again, what we need to know is width times depth times velocity is discharge. I'm throwing these concepts out at you here in this talk. I encourage you to read the USGS paper. It's about 3 or 4 pages long, and it goes into this, and so you can kind of digest it at your own time. But you can imagine that as the stage of a river, as the depth of the water increases, that means there's more water flowing. So the depth of the water, how high the water is in the channel, is also called the stage of the water. That's another term that's used, the stage. And so you can imagine pretty easily, I hope, that as you add water, there's more water flowing in, the river rises, the stage increases, and the flow will increase. But this is called a rating curve that gives you the relationship between the stage in the river and the amount of water flowing in the river. So this is a difficult thing to develop, and for the homework assignment, I'm asking you to go onto the USGS sites and onto the Sacramento County Flood Agency site and check out different gauging stations and look at their rating curves and look at how much water is flowing through the rivers. It's kind of interesting. But this idea of a rating curve, it's called a rating chart. It tells you that when the stage goes up, so there's 5 feet of water in the creek, and there's 10 feet of water in the creek. As that goes up, the flow of the river increases. It's not linear though. So like for most rivers, if the water stage goes up a couple of feet, it's not like the discharge just increases a couple of CFS. It really takes off. So this is a very important tool because it allows hydrologists to monitor how much water is flowing in the river by just looking at the stage. So you could take a river like this and just put in a float switch, or not a float switch, I'm sorry, a float of some kind, or a stream gauge, and say, hey, my stage is at 8 feet. Okay, I know if it's at 8 feet that I've got this much water flowing through the channel. It's kind of a simple concept, and again, there's some problems around these in the homework that I think will make this clear. And here is kind of the biggest deal of this unit, this concept of a hydrograph, which we're looking at here as a hydrograph. Again, this is written up in more detail in the USGS stream paper in Unit 4, but I'm going to cover really what I want you to know about this. It's a very important chart. It's kind of like the fundamental chart for hydrology. On the y-axis here, you have two things going on. You've got a rainfall intensity in inches per hour, and you've got stream discharge. So the rainfall intensity is shown in these little blue squares. This is, and on the x-axis you have time. So the story here is that you can look at a stream and how it's carrying water, and chart it over time. The base flow is this dashed line. And this would be like a groundwater coming in, and over time the water's just flowing along at this pretty steady CFS, pretty steady flow rate. On comes a rain event. And let's say a storm occurred. It took 2 hours or so, and then the storm stopped. And you could look at a stream that drains a watershed that had a rainfall like this, and watch how the stage of the river increases and the flow rate of the river increases sometime after the rainfall occurs. So the rain starts here, but it takes quite a while in this case for this river to increase its stage and its flow rate in response to that rain event. These relationships here, this is a hydrograph for a river, tells you a lot about the watershed. How much flow in the river do you get from a given rainfall event? And you can read that off of a chart like this. What I really want you to be familiar with is what this chart looks like in a developed versus undeveloped watershed. So again, this is in that same reference, so give it a good read after this talk if you need to. But the concept here is this compares the hydrograph of a creek before and after development. So here's the same blue chunks of rainfall. This would be rainfall intensity. So it rained this many inches per hour, here, and then it stopped raining. Before development, this is what the river did in response to that rain. It rose up, it peaked here, and then it dissipated back down to its base flow. After development, let's say we took a watershed that was forested or pasture or undisturbed somehow, and then we paved it over, or we compacted the soil, and we got all that nasty surface runoff that we talked about in the previous lecture, then the hydrograph will look more like this. It's going to rise faster because the water's now streaming off the surface instead of seeping in and coming out later. And the peak flow is going to be higher, and that's the key. Because the stream in this natural state from a rainfall event like this would peak at a lower level than after development. More water that falls from the sky ends up in the creek faster. That gives the creek water more energy. And from the previous talk, what does the river do with that energy? It digs into the stream banks and erodes further. So I would just flat out ask you, I'd give you a chart like this dashed line and say this is a typical hydrograph for a river. Draw a hydrograph for this same river system after development, just to drive this concept home, because it's really important for what's going on with our urban creek. I'm going to also introduce here, and it's written up more in the homework, this concept of the rational method to actually estimate how much runoff that you might get from a rainfall event. And this is a very often used and powerful little formula. It really only works for small watersheds, say a watershed that's about 200 acres or less. But we're using it in this class just to, again, drive these concepts home a little bit. So this just says, now, this is Q peak. This is the peak discharge of a river. This tries to calculate that. You can imagine that hydrologists are interested in this peak because this is what they design culverts for and all that. So this gives you an estimate of that peak discharge in cubic feet per second, given the area of the watershed and the rainfall intensity, and then the C factor. So this is, again, this isn't something to memorize. I will ask you some questions about this, but I'll always give the formula and the units and the numbers, frankly. I just want you to understand this relationship. It's pretty straightforward, I think, in that you can imagine if the watershed is bigger, if this area is big, you're going to have a bigger peak flow. More area is draining to the river, and so it's collecting more water, so you're going to have a bigger flow rate from a storm. The rainfall intensity is inches per hour, and again, I'm hoping that the homework assignment where you go online at the SAC flood site and download some of this data and play with it, you'll get a feel for rainfall intensity. But here again, if it rains really hard, you're going to get a higher peak flow resulting from it. And this is the last term, this C term. It doesn't have units. It's just a coefficient. And you can see here in this simple table that the coefficient is low when you have forests, lawns, cultivated land. It's typically pretty low. And then if you go to rooftops and concrete, it's high. So the C factor ranges from 0.05 to 0.95, and if you for the same area of watershed and the same intensity of storm, if you increase the C from lawn to pavement, you're going to get more peak flow. So I think that's hopefully intuitive to you now. And again, this equation is not here to confuse. It's to kind of drive the point home and play with the numbers and see how it works. I earlier mentioned this business of levees and how we have built levees to prevent flooding. Never mind these arrows. I'm not sure what the author is getting at here, but this is a nice cartoon of taking natural levees and enhancing them and making them taller. And what you're doing here is allowing the river to carry more water without hitting that flood stage. The problem with these is, again, how tall are they and what kind of storm event can they handle? And if you build up a levee like this and it does flood, then you're going to have a much, much, much bigger flood. Naturally, I mean, we do build these levees because we like to live on the floodplain here. The soil's nice, the land is flat, it's typically pretty well drained. So we either farm it or live on it, and so then we build up levees to prevent the natural flooding cycle from occurring. Again, the problem with these, and we'll cover it in the Delta area much more, is big rain events where the levees can't handle the flow. So instead of flooding every 2 or 3 years, you might flood every 100 years, but it's going to be a wallop of a flood, basically. And I wanted to end this talk by just touching on a couple of things: the levee system that we have here in Sacramento and the YOLO bypass. So this is a map. Here's Sacramento down here. Here's the Sutter Buttes. It covers a large part of the Sacramento Valley. All these red lines are constructed levees. So we've taken the Sacramento River and its tributaries, and we have built up levees to prevent the natural flood cycle so that we can cultivate and develop the land around these rivers. One such system, though, that is pretty ingenious and does a lot of work for us for flood control is this YOLO bypass. It is the Sacramento River moving through, and here's the town of Sacramento right here. What this YOLO bypass does, they just put in a weir at a certain elevation, and when the stage of the river gets too high, the water then diverts and goes to this bypass, and it bypasses this part of the Sacramento River. And notice these numbers. When flood stage is happening, the Sacramento River can't really take more, even with us mighty levees, than about 110,000 cubic feet per second. After that, it's going to flood. Notice how much water, though, that the YOLO bypass is carrying during the flood stage. 5 times as much water goes through the YOLO bypass as the Sacramento River. So when this was designed, I believe it was in the 20s, the area wasn't so developed and there wasn't so much pressure on land use, and you could go ahead and dedicate this whole area for flood, allowing the river to flood naturally, and really doing a great deal of work for us protecting Sacramento from flood. So I just wanted to give a shout out to the YOLO bypass. This is what it looks like in plan view. This is the Sacramento River, all leveed up, high, 20-foot levees. And here's downtown Sacramento. And here's the Fremont Weir, where it takes Sacramento River water and says, come over here, I got you. And here's 500 CFS moving through here, while 110,000 CFS moves through the river. So I hope that's interesting and helpful to you. Again, please do the extra reading and check out the problem sets in the practice problems in Unit 4.